Okay, good morning, everyone. So this is a joint work with Sérgio, Miguel, and Umberto, who unfortunately could not be here today. And I'll start with an overview, and then I will enter in more details. So here in this work, we study a family of finite valued logics, okay, whose goal is to model indicative conditionals. And these are like natural language sentences, if then, that talk about what could be true. And this is as opposed to counterfactuals, like they're not talking about events that are not possible to happen anymore. Just to give a quick example, I'm not it's going to be obvious that I'm not the specialist on indicative conditionals. But for example, if the train's on time, we will be home by 10. This is an indicative conditional. But if we have said, if the train had been on time, we would have been home by then. This is a counterfactual. And in this work, we take this big family of finite value logics and provide analytic calculi and finite axiomatizations for all of them in a uniform and modular way. But in this talk in particular, what I want to do is to briefly present the logics. But what I want really to do is to illustrate and advertise these methods because they are general enough that can be applied to other families of finite valued logics. And basically, the method can be summarized in this diagram. So we allow finite valued logics that are determined by finite families of logical matrices. Then we use partial non-deterministic semantics to pack all the matrices in one single one. Then we use an algorithm that axiomatizes, that produces an analytic calculus. And if you don't like the kind of calculus that we produce, you prefer Hilbert calculus, the traditional ones, we also have a conversion from these ones to Hilbert. And I mean, in particular, if you're interested in algebraic study of these logics, as Umberto and Miguel are, having Hilbert calculi is nice. And also, if you're interested in the study of combination of logics, Hilbert calculus are also interesting. So this is basically what I want to present. So the idea of these logics of indicative conditionals is that many sentences of natural language that involve these conditionals, they can sound pretty absurd if you use the material conditional, the classical implication. And many people, many years ago, noticed that one of the reasons is that when the antecedent of the implication is false, we automatically assign true. And the proposal is that instead of doing that, we assign a new truth value, 1/2. Natural proposal. And the point is that we are committed to this in blue. So whenever you have 0 antecedent, you have the intermediate value. Oops. But also there are open interpretations for what happens with when the antecedent is the intermediate value. So many authors came with different implications for that. And I'm not going to try to go for the intuitions. Maybe there are no intuitions for that. But also something that they really try to do is to don't go too far, let's say, from classical principles we'd like to keep. So I understand that the design is also fine-tuned for that purpose. Also, in some cases, not only the implication changes, but even the conjunction and the disjunction. So in particular, this logic, OL, ordinary discourse logic, was proposed by William Cooper in the 70s, which basically came up with, I don't know, 200 examples of sentences involving conditionals that sounded like absurd. And by proposing, in his logic, he managed to get rid of these examples. And these were examples like that were valid in classical logic, but didn't sound nice in natural language. But also the converse was also true. So in this logic, kind of you have the consecutions that you want, and you remove the ones that you don't want. Also, I must mention that whenever I say negation here, is going to be the strong clean negation. So 0 goes to 1, 1 goes to 0, and the intermediate value stays there. So it's a fixed point. So the family of logics that we study contains basically all of these. These 4 logics were presented independently, and they are given by these algebras. Let me see what I can talk about them. So all of them have this negation that I mentioned. Most of them use the strong clean conjunction disjunction. And here, the ordinary discourse changes everything, basically. The designated sets usually contain the 1/2 because we want to keep the tautology of classical logic. I think that was the main reason for them. And we also study logics starting from these, but changing the designated elements. So your standard of what is true. And also we study logics of order obtained from these algebras. And so they were proposed many decades ago, but recently Umberto and Miguel started studying them from the algebraic perspective. So we have the algebraic logic studies of them. And I can mention some of these properties. For example, df is a conservative expansion of the logic of paradox. It fails to be algebraizable and self-extensional. And we consider variations of it, as I said. OL in turn is algebraizable, and it can be obtained from classical logic just by adding 4 axioms. And we can also consider the logics of order of OL. And inside OL, you can define actually 3 orderings. So there are 3 different standards of truth that you can have. And this logic F is definitionally equivalent to the logic Cn that I mentioned before. And both of them are algebraizable. And we also consider variations of them. And according to Umberto and Miguel, they have been trying to axiomatize these logics via algebra. And they said that it's a very challenging task. Because the transformers are very complicated, so the axiomatizations you get are very difficult to deal with, if you manage to get them. And also for the logics of order, there is no systematic way of obtaining them, so you have to do like case by case. And in this work, we actually do at once, we obtain analytic calculus for them, and also traditional calculus. So traditional axiomatizations using a uniform and modular approach. So as I wrote here, the kind of calculus that we produce is what we call multiple conclusion. This kind of systems were introduced by Schmidt and Smiley in 1978. And I'll try to exemplify how they work. But first, I would like to talk quickly about what are these partial non-deterministic matrices that I mentioned. So these structures, they have one algebra and one set. It's called the designated element set. But this algebra is not just an algebra, it's a multi-algebra. And by that I mean that you have the set of truth values as usual, but the connectives are not interpreted as functions, but as multifunctions. So the output is a set of truth values instead of only one. You can also have empty outputs, okay? So you can see them as a generalization of truth tables. As I said, D is a set of designated truth values, like our standard of truth. And we define a logic over a Pn matrix. Like this, we say that a set psi follows from phi if we don't have a counter model for this statement. So if there's no valuation on M, such that all the elements in the premises are designated and the ones in the conclusion are non-designated, okay? And that's what we call a logic, which can be a bit weird if you're more used to Tarskian logic, so single conclusion. But the point is that we can recover the single conclusion from this. Just to give a quick example of what a Pn matrix looks like. So what is different from a matrix is that in the truth tables, you can have more than one value in a cell, and you can have also empty sets here. And the usual notion of a logical matrix in many-value logics is just a total deterministic PN matrix. So total, you have no empty sets as outputs. Deterministic, you only have one value. So you only have singletons as outputs, to be more direct. And as I said, you can recover a Tarskian consequence relation from a multiple conclusion ones just by considering the singletons as conclusion. And when I talk about the logic induced by a family of matrices, I talk about the intersection of the logics induced by each of them. Okay? So this is the sort of semantic structures that we use. And this is the sort of calculus that we use. So I'm going to define them by this example. So this is a calculus for classical logic, propositional classical logic. It's a multiple conclusion calculus because, as you can see, you can have multiple formulas in the conclusion. And you can also have the empty set as a conclusion. This, for example, is an explosion rule. This is like excluded middle. And what else can I say? So yeah, this is how the rules of this calculus are. This is how a derivation of this calculus look like. So we talk about the logic induced by a calculus. And to prove, for example, that P implies P in this calculus, what I do is that I build a tree using the rules. And in every branch, I have to end with P implies P. It's not like TABLEAUX that you have to start with a negation or something false and you get to close the TABLEAUX. Here you want to get all the formulas that you want. Actually, it's going to be a set here, so at least one of them in each branch. So this is actually working like it's an internalization of proof by cases, if you want to think as the commas like disjunctively. And this is how we prove P implies P. So we use R9, an instance of it. So you open two branches because you have two formulas here. And from here, you use R8. From P, you can get to P implies P. This is how we prove this, that not P, comma not Q follows from not P and Q, using the same idea. And one detail is that when you get a formula and its negation in a branch, so the branch contains all the formulas since the root, right? Then you can use, for example, this rule R10, and when you have an empty set, you just put a star to indicate that you can derive anything, so the branch is also closed. And because we get not P here, not Q here, and star, we managed to prove this statement. So this is how derivations of these systems work. And what is nice is that this calculus is analytic. That means that we only need subformulas of this statement, for example, this one, to be considered in proof search. And this induces a decision procedure because I can start with this one in the root and keep applying rules. And because I have a control over the search space, we're fine. And I can ask, but what are these relations, right? So just to be very clear, these relations are generalized consequence relations. They're binary relations on sets satisfying properties of overlap, dilution, and cut. And they can also satisfy substitution invariance and finitariness. And this is like a generalization of the usual Tarskian consequence relation properties. And if you have a GCR and you have a calculus that induces the same, we say that that GCR is axiomatized by the calculus or that the calculus axiomatizes it, just to be clear on terminology. Also, if you have a class of matrices, a family of matrices that induce the same GCR, we say that this family characterizes or determines the consequence relation. And also for every GCR, we can talk about its single conclusion companion just by focusing on the singleton conclusions. So you can recover that. And for that reason, if we have a calculus that axiomatizes the GCR, we also have a proof system for its single conclusion. So in particular for matrices, for many-valued logics, if you're studying the multiple conclusion version of it, the single conclusion one, that is the most usual logic that you talk about, is just going to be its single conclusion companion. So by studying in the richer framework of GCRs, you're also studying the one in the simpler. Okay, and then I mentioned that we can use an axiomatizer to produce calculus automatically, but that works under a condition that the matrix has to be monadic or monadic. And I'm going to explain quickly what that means. So if I give you a matrix, and I give you two values, I say that a formula is a separator for these two values. If when you plug this value in the formula, one of the values in the formula, you go into one designated set, to the designated set. If you plug the other one, you go to the complement. So that formula separates this pair of truth values according to D. Okay? We say that a set isolates a value if it contains separators for this value and all the other values in the matrix. And we say that M has a discriminator if you have a family like this, so pairs of sets for each value, such that for each value you have the union of the sets isolating X, so you have separators for X. And all the formulas here put the value X in designated set, and the formulas here put it on the non-designated set. So whenever you can have this sort of thing, we call that M is monadic or sufficiently expressive. We have multiple terminologies for it. But basically that means that you can characterize all the values of the matrix using formulas. So for example, if evaluation puts not P in designated set and P in non-designated, we know that the evaluation assigns 0 to the formula. That's one example, and you can do it for all the others. And we say that a proof of a statement is theta analytic when it contains formulas that are in the subformula of the statement, but also formulas that result for plugging the subformulas for P in the set theta. So theta is a set over formulas over a single variable. And we say that the calculus is theta analytic when every statement that you can prove in it has a theta analytic proof. Okay. And then we have this theorem. Every time you have a monadic Pn matrix, you can effectively generate an analytic calculus for it. And it's going to be analytic with respect to the set of separators. And this calculus is going to be finite if the matrix is finite. It turns out that the algorithm is modular in the signature. So if I add more connectives, it preserves the monadicity. So that's also good for axiomatizing expansions and fragments of these logics. And now you might think, okay, I have this multiple conclusion calculus. How do I get a Hilbert calculus from it? For that, you also have some extra conditions. In particular, you need to have either a disjunction or an implication in your logic, which are connectives satisfying these properties. So if you have them, you can convert a multiple conclusion calculus into a single conclusion one, preserving finiteness. That's what I said. And turns out that all the logics that we considered, they have a disjunction. So for all of these logics in this family, we could convert a multiple conclusion axiomatization for a single conclusion one. And very quickly, I'm going to just exemplify what we did for this family of logics using these methods. So for logics that are determined by a single matrix, we don't need to do that first step of packing that I mentioned. We can only use one matrix. And all of these logics have the same negation. And this negation is enough to prove monadicity for them. So you can start just from the negation fragment and add the other connectives, which are axiomatized by these rules, very simple rules. And this calculus is analytic with respect to this theta. It means that to prove something there or to search for a proof, you only need to look for proofs with subformulas or negation of subformulas. This is the logic F. If you want to axiomatize the logic OL, you just need to change the connectives for those of OL. The negation rules stay the same. And if you want to change D equals, for D equals 1, it's going to be similar. The discrimination is going to change. Obviously, the rules are going to change, but not drastically. And if you want for D equals 1/2, you need to use P implies P as a separator instead of negation. So this way we covered all the logics that are determined by a single matrix. And very quickly, when I say logics of order for an algebra, I mean these logics that preserve degree of truth. So basically, we say that phi follows from gamma if phi cannot have a lower truth standard than the formulas in gamma. And this can be equivalently presented by the family of matrices over the same algebra, but the sets D are the principal filters of that algebra. And when the algebra is finite, you're going to have this family is going to be finite as well. It turns out that these logics fail to be characterized by a single matrix. We can prove that usually. And it turns out that all these algebras, they have an order. And then the question is how to axiomatize them. And the idea is that, and this is an example. Let's say we have this family with two matrices. And the idea is that we're going to pack these two matrices in a single structure using the partiality that I mentioned before. And this is the new semantics that we presented for this logic, which is a 4-valued matrix that induces the same logic as that family. And this matrix is monadic, so we can axiomatize them. We can axiomatize the logic now using this structure, because we could not do before, because the algorithms, they don't deal with families of matrices. And to see how it works, this packing, if you take the submatrix obtained by deleting this value 1 minus, and you focus only on the blue part, you're going to see exactly that it is this first matrix here. Not is, but it is isomorphic too. Okay. Similarly, if you delete the 1 plus, and you focus only on the red, this is a matrix that is isomorphic to that one. And for PN matrices, we have this nice result that the logic induced by a PN matrix is the intersection of the logics corresponding to their maximal total components. Total components are components that do not have like empty sets as outputs. And turns out that these two matrices, the red and the blue, are the maximal total components of this one. So that's how you do the packing, and then you can do it for more than two matrices. So finally, just summarizing, yeah, we took this family of logics that were hard to axiomatize from usual methods, from algebra, and we showed how you can do it systematically, uniformly, and also how to axiomatize expansions and also fragments of it. I have a prototype implementation of this axiomatizer. It's available here, it's open. I implemented in my master's, and then along the years I was like keeping it, solving some bugs. And if you have a family of many value logics that are like these ones and you'd like to understand a bit more how they work, the specification of the logic is very simple. This is how you specify a PN matrix. These are like the truth tables. You just specify how the inputs and outputs work. You specify the set D, the values. You can give any names to them, hopefully. You can also specify the discriminator in table format, just as I did in the presentation. And then you run a command line interface in Docker. So you run in NOS, basically, without problems. And you generate a PDF with the list of rules. You also can control some parameters like simplifications you do on the calculus and stuff like this. But yeah, I think this can be helpful if you want to do things similar to this. Unfortunately, the packing of the PN matrix is not implemented, so that you have to do by hand. Yeah. So I will leave, I'm not going to leave this question, but it's like, you can deal with it. But let's open for questions.